change of variables formula lets you change integration over a complicated looking region to one which is much simpler. And it's stated here, it says that if you have a mapping function that goes from one region in two-dimensional space to another region in two-dimensional space that is one-to-one, and that just means that two different points are taken to two different points, and is continuous, then the double integral of f over d, the target domain, the complicated domain, is equal to the double integral over d naught, the simple domain, of f of x of uv, y of uv, times the absolute value of the Jacobian. So when we're seeing it for the first time, it looks yucky, but it's really just the two-dimensional version of a U substitution from first semester calculus. So we did one example in class. Let's look at another example. So here our difficult domain is D, the parallelogram that we see here. And we can see why this is difficult. I can look in this picture and see that the x variable goes from 0 to 5, but we don't actually have y values for all of the x values. So, or rather I should say that for each particular x value, it's just complicated what y does. And because of the domain has this shape, it would be difficult to just try to find a simple limits of integration formula to get this. So instead, we're going to simplify it by using the suggested map g of uv to turn it into an integral over the square 0, 1 cross 0, 1. So that's just the square with vertices at 0, 0, 1, 0, 0, 1, and 1, 1. So we're going to change integration over this parallelogram D into 1 over the simplest square where where u and v both go from 0 to 1. So we're going to let g, as suggested from the square to our domain D, be defined by x of u of v equals 5u plus 3v, y of uv equals u plus 4v. And it's pretty easy to see that this map does map the square onto the parallelogram. When u and v are both 0 at the origin, then x and y are both 0. When v is 0 and u is 1, then you're at 5, 1. X is 5, y is 1. When u is 0 and v is 1, then x is 3 and y is 4, and you're at that vertex of the parallelogram. And then when u and v are both 1, then x is 8 and y is 5, as suggested in the picture. So this mapping G takes the very simple domain, the square, onto the parallelogram. And then the change of variables formula lets us change integration over the parallelogram into 1 over the square. And what function are we trying to integrate over the parallelogram? The function xy. So right here, this is what we're evaluating, the function xy over this parallelogram D. So first we have to find the Jacobian. Well, the Jacobian, remember, is the determinant of the matrix dx du, dx dv, dy du, dy dv. And when you calculate that here, it's just the constant 17. And that we don't even need to take absolute value because that's already positive. Now in this particular example, that Jacobian is a constant function, but in general it might not be. So we apply the change of variables. So the integral over d should be the double integral over d naught. Well, d naught, u goes from 0 to 1, v goes to from 0 to 1. X of u of v is 5u plus 3v, y of u of v is u plus 4v. So the function f of xy equals x times y. F of xy equals x times y is just 5u plus 3v times u plus 4v. Then we multiply by the absolute value of the Jacobian, that's 17. And I'll leave it to you to multiply all that out and see that you get 2329 over 12, which is much easier than trying to find limits of integration for the original parallelogram. And before we close this example, one quick note. It's not too hard to see that the integration in polar coordinates is really just a special case of the two-dimensional change of variables formula, and integration in spherical coordinates is a special case of the three-dimensional version of the change of variables formula. So we haven't spent a lot of time on change of variables, but hopefully another example is useful.